Okay, this next example is actually example 2 in your book on page 129. I think it's a very good problem that I wanted to go over. If you want to read it on your own and not watch the video, that's completely fine, as long as you understand the process and what's going on. Okay, so let's start. Find the general solution again of this. This is a fifth order differential equation. So we have 9y to the fifth, 6y, and that's a 4, plus, that's a 4, plus y to the third equals 0. And I'm going to make that nicer. It's going to bug me. So 4. Okay, so again, we need the characteristic equation. And our characteristic equation is going to be 9y, not y, I keep writing y, 9r, right, for roots, 9r to the fifth, minus 6r to the fourth, plus r cubed. Right, this is our associated characteristic equation to our given differential equation above. Okay, can we factor? And yes, we can. And again, you always want to ask yourself, especially for the test, because some students make it harder than it is, can I factor a GCF? Anytime you factor a polynomial, your first step should always be, or your question should be, can I fact a greatest common factor? And I can, right? There's definitely an R, well, at least 3 R's, 3 factors of R in each term. So I get 9r squared minus 6r plus 1. Okay, if you distribute that r cubed, you should obtain the same polynomial. Okay, so we know we're going to have some multiplicity here because we have that, let me get my pointer, right? There's our r cubed. So I know my multiplicity is going to be k. Well, in this case, it's going to be 3. But can we factor, so let me just write r cubed. Can I factor this guy? And obviously, if you're looking at the book, you can factor it. This is actually a perfect square trinomial, right? Trinomial, because 3 terms. And it's a perfect square because, you know, if you square that, well, this is a perfect square, right? 9, 3 times 3, 1, 1 times 1. And I mean, if you don't remember this actual terminology, it's fine. I mean, you can just start factoring. Okay, 3r times 3r is 9r squared. You can try 9r and r, but it's not going to work. 1 times 1 is obviously 1. And I know these guys are going to be negative, right? Because the inter, right, you're really unfoiling. Again, that's just what factoring is. This guy is negative 3r. Well, this times this is negative 3r, so that gives me negative 6r, which is what I want. So let me just go ahead and rewrite. So r cubed times 3r minus 1, and notice they just squared it, right, because it's really just a repeated factor. And again, these, your exponents, right, should add up to the number of roots that you're going to obtain, right? So it matches. 2 plus 3 is 5, and obviously our differential equation, our order is 5. And again, they can be distinct, but don't necessarily have to be. Okay, so again, we know we're going to have some double and triple roots. So maybe let's write that down. Triple root, right? And we know we're going to have a double root, right? And or repeated roots. So here we're going to have, so maybe let's write our multiplicity. I think I want to say use green, I'm not sure, but my k is 3. So multiplicity, and this guy, right, that's going to be, it's a different multiplicity, right? K is going to be 2. So multiplicity. Okay, so now writing that out. Well, I mean, again, r cubed is going to be 0 using the zero factor property from algebra, or 3 minus 1, right? Either this factor is equal to 0 or this factor is equal to 0. And obviously, if we solve for r, we get, right, you cube root both sides, you get 0. And again, we know we have really 3 of them. And then this guy here, if you want to use the square, there's a couple different ways you can do it, but I mean, I'm just going to take the square root of both sides. 3r minus 1 equals, well, plus or minus the square root of 0, but I mean, this doesn't matter because if I give you $0 or I take away $0, I'm not really giving you or taking any money. I'm not taking anything away. So, I mean, 0 is neutral, so we can omit that. And this just says algebra, so r is a third. Okay, so we have, well, 2 roots here, but again, there's really 3 of them here, and here there's really 2. So let's use our repeated roots theorem from the last example, right? Theorem 2. Okay, so remember, let me write this a little bit big here. K is 3 in this case, and then of course K is 2 in this case, right? Because here we have a double root, right? This is really repeated 2 times, and here this is a triple root. So according to our, let me go ahead and write this. Okay, so well, let me go ahead and write it out. So the general form is C1 plus C2x plus C3x squared plus dot 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 plus CK x to the k minus 1 times e to the rx. Okay, our focus is, excuse me, is this k. Well, we have 2 k's. So if we work with the first k, okay, if we plug in 3 right there, 3 minus 1 is 2, right? So that really means that I only need, right, I only have to go up to the second power. So this is going to be C1 plus C2x plus C3x squared. And remember this guy, I mean, when you, well, let's go ahead and write it out. Again, this doesn't hurt. Okay, e to the r times 0. Well, what's my r? My r is 0. Well, 0 times x is 0. But again, this is just a big 1. So, I mean, technically it doesn't matter if you write this part out. I mean, I want you to understand it, but you still just get times 1. So I have C1 plus C2x plus C3x squared. Okay, so that is the solution to that triple root that we had. So plus, now let's use our k equals 2, right? Our multiplicity of our our root of our root, that's 1/3, which is obviously repeated. Okay, so here we're just going to go up to, it's going to be C4, right? Because we have 1, 2, 3, and the next one is 4. Whoops, e to the r, our r4 of x, right? Or the next root rx, but our r is 1/3. So 1/3 of x plus C5, and again, we need an x here because you have an x in the next term, right? This is like my C4 and C5 that we're using. And then we have e to the 1/3 x, right? Or they write x over 3. So that is your final solution, right? Y of x equals, I'm going to write this nicer, C1 plus C2x plus C3x squared plus C4e to the right. You can write this as x over 3 plus C5x e to the x over 3. Okay, so that is our final solution. One thing I do want to say, which is I think important. Okay, if you're wondering, where are they getting this you know, this expression times e to the rx for the repeated roots. Well, if you remember in section 2.2, I did talk a little bit about it, but just in case you forgot, if you distribute this e to the rx to each guy, okay, well, this guy is really going to be it's e to the 0 for our, in this case, our r equals 0. So this is really 1. So you're really saying c1 times 1 plus c2 times 1. Or if you remember right, this usually we write this as c1 e to the, you know, r1x plus c2 e to the r2x and so forth. I mean, this guy's not going to matter eventually because it's just going to be times 1. So if you're wondering, if that just confused you, then you can ignore it. But again, they just really factored out an e to the rx. Okay, that is example 2 in your book.